Let's consider the function f of x equals x squared. With the derivative, I'm interested in knowing the slopes of tangent lines to this graph. And let's go ahead and pick the input 1, which also has an output of 1 because 1 squared is 1. I'm wondering if I draw a tangent line at this point, what is its slope? Well, first of all, you have to ask, what is a tangent line? A tangent line to a circle in geometry is described as a line that touches the circle at just one point. It's like it kisses the circle at just one point, just a peck. That definition doesn't quite work for arbitrary curves because your arbitrary curve could come back down again, even close to the point in question. So it's not good enough to just say it touches the curve at one point with a curve. A better description of what the tangent line is as what's called the best linear approximation to the curve at the point. Intuitively, what that means is if you zoom in near this point, like with a microscope, closer and closer, the tangent line is the line that the curve looks more and more like as you zoom in closer and closer. In fact, let's go ahead and do it with the calculator here. X squared is our function. Let's pick our initial window to be 0 to 2 in the x direction and say 0 to 2 in the y direction. Okay, it's a curve, not a straight line. It's hard to say what the tangent line looks like at this point. Let's zoom in closer. Let's go 1.9 to 2, excuse me. Tab up. 1.1 here, 0.9 here, and go 0.9 and 1.1 as well here. So I'm zoomed in on a window very close to the 0.11. The graph is going to look straighter. In fact, it looks like a straight line. That is technically still a curve, but it's so close to a line, it effectively is the tangent line. That's the intuitive idea. I'd like to know what the tangent line is. I'd like to know its slope. I certainly know it goes through the 0.11. If I could find its slope, then I could find the equation of that tangent line. The slope of the tangent at x equals 1 is called the derivative of f at x equals 1 and is written as f prime of 1. It is defined as a limit if this limit exists. We're running low on time, so I have to go kind of quick here. We will go slower on problems like this next week. The limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. Real quickly, what is that? H is imagined to be a small number. Could be positive, could be negative. I'm drawing it to be positive. This quantity represents the slope of what's called a secant line. Secant line between these 2 points on this graph. That quantity that I circled without the limit sign is the slope of this red line that I just drew right there. It's rise over run, though that's not immediately obvious. If I let h go to 0, meaning 1 plus h goes toward 1, that red line will get closer and closer to the other red line I drew, the tangent line. In fact, this limit, if it exists, is the definition of the slope of the tangent line. But does this limit exist? Let's try to compute it. What's f of 1 plus h? I need to go to the formula for f and replace x with 1 plus h. Get this right. I got to square the entire expression 1 plus h. That's f of 1 plus h for f of x equals x squared. What's f of 1? It's 1 squared. Of course, that's 1, but I'll write it as 1 squared. What do I have here as I continue simplifying, including doing the FOIL method here? I have really a function of h. And if I graphed it as a function of h, it's going to have a removable discontinuity, it turns out, at 0. This limit will end up existing, and it'll be equal to 2. Listen real carefully. So I did that calculation fast because we're almost out of time. What did I do? First of all, I expanded 1 plus h quantity squared. I FOILed it and got that. Don't forget to subtract 1. I canceled the 1s. Then up top, I had these two terms left. They both have a common factor of h that can be factored out. Then I divided out the h's and got this. And that's a nice continuous function at h equals 0. I can find this limit by substitution and get 2. As functions of h, these two things here and here are equal as long as h is not 0. This one has a graph that's a straight line with no holes in it. This one has a graph that's a straight line with a hole in it. A removable discontinuity at h equals 0, but the limit exists because they're equal. And this one has a limit that equals 2. And that value 2 is the slope, is the derivative, and is the slope of the tangent there. That's the slope of this red line. We'll do plenty more calculations like this next week. Have a good weekend.